Hello, and welcome to today's webinar, Comprehensive Compressed Air Assessment, a 5-step process, brought to you by Plant Services and Taser Compressors. I'm Christine Lefebvre-Grace, Managing Editor of Plant Services. First, let me express our appreciation to you for joining us today. This webinar is sponsored by Taser Compressors, a global force in compressed air system solutions committed to maintaining the highest quality standards and delivering products that are built for a lifetime. Before I introduce our speaker, there are a few housekeeping issues that I'd like to review. On your screen, you should have several primary sections. The upper left or audio control section allows you to adjust the volume of this presentation. Just hover over this section until you see the audio volume control and adjust the volume to your preference. To the right, in the largest section, is where today's presentation slides will be displayed. Under the slide window, you'll see a chat section where you can chat live with fellow audience members. In the handout section, you'll find a variety of resources available for download. We'll get to as many of your questions as we can during the Q&A session that follows this presentation. At the left of the slide window, you'll see the question and answers box where you can type a question for the presenter at any time during today's webinar. If we're not able to get to your question during the webinar, or if you have a question after the webinar has concluded, Neil and Taser will be able to answer these directly later, so feel free to ask away. Finally, at the bottom of your screen, you should see icons for additional features. By hovering over each icon, information about the icon will be displayed. If you're having technical questions, you can type your question or concern in the question and answers box, and one of our technical engineers will assist you. If you need a better view, you can enlarge a section by clicking on the box in the top right corner of the section next to the X. If you accidentally close out of a section, you can get it back by clicking the Restore button at the bottom of the screen. It's located to the left of the icon. We want to remind you that this webinar will be archived, and we encourage you to direct your coworkers to the recorded presentation. Finally, at the end of our presentation, we'll ask you to complete a very brief survey to give us the feedback that we need to improve our webinars. Now I'd like to welcome today Neil Meltrutter, Engineering Manager at Taser Compressors. Neil is a widely recognized expert in compressed air management and a familiar voice to Plant Services audiences. Neil, thanks for being here again. Take it away.
Great. Thanks, Christine. So compressed air is a valuable part of every plant. It's why Plant Services shares webinars with compressed air topics regularly. I'm sure you don't consider your compressed air system an island like I've shown here, but really, when was the last time you checked in? How was your compressed air system actually operating? What better way to find out about your system than to do an audit? Certainly rhetorical questions here right now, but today we're going to focus on compressed air audits or assessments. Why to do them, the 5 basic steps, and setting expectations. Manufacturing facilities are constantly looking at operating costs and production. Here's one way to break out the types of wasted resources in industrial production. These are all areas that plants aim to minimize to some degree. Your compressed air system and equipment impacts all of these areas. Compressed air is only one facet of plant operations that impacts these areas, but in some plants, it might play only a minor role. Generally speaking, compressed air is mission critical in nearly every facility. It powers more than 70% of all manufacturing activities. If compressed air is not delivered at the right air quality and quantity, production costs increase as both plant equipment function and production quality can be compromised. The U.S. Department of Energy estimates that air compressors use as much as 10% of all electricity generated in the United States, and that as much as 50% of all compressed air demand is for non-productive uses, which includes leaks, artificial demand, and any improper, inappropriate, or inefficient uses. Air leaks alone account for 25 to 30% of compressed air use, and on top of that, additional power is wasted in the creation of compressed air through improper sizing, pressure selection, and controls, which also has significant impact on equipment reliability. On top of all that, electricity for the compressor accounts for 76% of life cycle cost, whereas maintenance and purchase price end up being about 12%. By understanding your compressed air system's demand, companies are able to identify potential compressed air savings. Many plants have 30% in energy savings potential, so keep those things in mind. How do you know if your air system is delivering air at the right quality and quantity? And how do you know if you're wasting air through improper sizing, pressure selection, and controls? You got it, an air demand analysis. An air demand analysis or assessment, and we use those terms interchangeably, though they are technically separate. Here we'll use them interchangeably, so keep that in mind. Using an assessment or air audit gives plant owners and operators a clear picture of how their system operates, as well as how much energy it consumes, if the system is reliable, if it has the right air quality, and the most telling point is an air audit is going to tell you how efficiently the compressed air system is actually running based on a key performance indicator, or KPI, called specific power. Using air audits on a regular basis or simply reviewing your compressed air deliverables regularly can help you make sure your compressed air system is always running at its best. Not that there are many resources available showing how data monitoring from a master controller can be a powerful tool. So there's a lot of information out there right now, and including data analysis from master controllers or directly from your station controller for your individual compressor to tell you how your system efficiency is actually playing out. So we're going to check out those links at the end of the webinar for more information. Many air system owners, they don't have a clear picture of how their system operates or how much energy it consumes. So, hence compressed air audits, great way to baseline the system and visualize what's happening before trying to make improvements or adding compressors to accommodate expansion. An audit can help you build an energy and demand profile to help you see in black and white what your system capacity is and what your productive demands are. A good audit will also provide actual power consumption for your compressors, as well as clues to non-productive loads such as leaks, timed electric traps, etc. Non-productive loads waste energy 24/7 as long as your compressors are on. So the data collected can be used to determine that optimal mix of compressed air equipment, including what you already have and maybe some new equipment, as well as plan for future expansion. An air audit from a competent compressed air professional is a first step in determining compressed air efficiency. And combining this audit with a leak detection service, as well as evaluating each air user, will improve overall system performance. So if you're bringing in an outside party to perform this service, make sure your vendor is not cutting corners and that you understand these things. Number one, what's the goal from your air demand analysis? Such as, do you have low pressure points in the plant? Do you have air quality issues? Also, figure out the necessary steps for a vendor to provide an accurate system snapshot, as well as the importance of controllers in any optimization plan. And finally, know that systems can always be improved, even with new compressors. Every process can be broken down into steps. Granted, there'll be more detail in each step, but these are the top 5. So number 1, conducting a site survey or walkthrough of your facility. Number 2, measuring and quantifying power versus flow. Number 3, understanding these system dynamics, how pressure affects operation, and identifying ways to improve the system. Number 4, implementing those recommendations. And number 5, verifying the performance. When conducting a walkthrough, it's important to list and understand all the equipment in a compressed air system before installing any measurement devices, so that number 1, the devices are properly placed, and number 2, basic system dynamics are properly understood and accounted for. The person responsible for collecting information should note environmental conditions, physical layout, details on all air system components, including air treatment, which would be dryers and filters, as well as piping, storage, and controls. Take pictures. You'll want to reference these later on in the project. And while you're there, do some spot measurements of pressure throughout the facility so you can see what the initial pressure profile is and if you really need to measure various points in the plant. Ask questions. In most cases, I recommend, or I ask the same question to multiple people in the plant. So engineering, production, maintenance, management. What I find is even the guy driving the fork truck who's doing shipping and receiving, they notice something about your compressed air system, and technically they want to share it. So in many cases, you're going to get different responses to these questions, and it's just perspective, but it's going to help establish priorities for your project. At this point in the process, many assessors are going to combine this information into one document, and we call our document a questionnaire. Also, consider ancillary support systems during your walkthrough, like ventilation, electrical, and maintenance. These systems will often be overlooked and are more times than not part of the problem and the solution to improve system efficiency and reliability. Lastly, don't forget establishing goals, because you're going to come back to this in the verification step. Remember that the compressed air system isn't just the compressor room or rooms. During your walkthrough, make sure you take a tour of the entire plant and determine what are the most important areas, what items you need to measure, where, and how. These measurements should include multiple pressure points along with flow power. Additional measurements might include compressor operation, such as load and service hours or general alarms, ambient conditions, dryer operation, or even pressure dew point. Again, it depends on the goal of your assessment. I mentioned this already, but getting out of the compressor room is key to understanding the system. The piping network, point of use filtration or dryers, the pressure profile throughout the plant, and how the plant's using the air encompasses the entirety of your compressed air system. The picture at right shows perhaps maybe an atypical compressed air system with multiple loops and various piping that you can actually see. In a lot of cases, you don't see these things, but this gives us an idea of what a compressed air system and piping breakdown could look like with a pressure profile. So we can see about 10 psi drop across air treatment in the compressor room. So at right, you see max of 102 pounds. That says 99 psi, and then to the left there in the compressor room at the bottom, it says 89 pounds. So there's your 10 pounds. And then all the way to the point of use at the top right is 87 pounds. So very marginal 2 psi drop in the main network to that furthest point in the plant. But you have an 18 psi drop from that main header to that point of use. So, why is that? Seems fairly excessive. Is it a regulator issue? Maybe they only need 59, 60 psi, or maybe the hose is too small. So these are things that observation you want to make during the walkthrough. Also, you want to look for high intermittent demand events in the plant, as well as any point of use air quality issues. What better way to follow these steps through than looking at a case study? This particular facility that we're going to review had 2 compressor rooms using rotary screw air compressors from 3 different manufacturers. Both compressor rooms are drawn into the sketch at right. The first room, which we highlight in red, had a 60 horsepower compressor with a refrigerated air dryer and other associated air treatment. This compressor was operating in modulation control. This type of control is very efficient at maintaining plant operating pressure with any small changes in demand. However, it can be very inefficient at part load demands, and we'll see that later on. You can also see the pipe network is shown in this sketch. It's made up of a multitude of black iron pipe, 1.25 inch, 1.5 inch, and 2 inch lines. Note that if you don't have a detailed piping drawing for your plant, you can take an evacuation layout of the facility, which are generally available everywhere, and overlay piping onto it, or simply take a screenshot from Google Earth. or you can create your own here, like you see here. Room 2 had two actually rotary screw air compressors, one 50 horsepower and one 75 horsepower. While both were operating modulation control, compressor 3 was actually offline during the testing period. And we gloss over the ratings of the refrigerated dryer and filtration, but you want to evaluate the rated conditions of this equipment versus your actual conditions, as this could also explain why your air quality may be compromised downstream. In addition, there are multiple compressor rooms like this. When you have it, like we've shown here, you want to ask why. Was it because a compressor came with a specific piece of equipment? Was it because one particular area of the plant couldn't maintain the necessary plant pressure? Generally, a fresh perspective can unlock long-forgotten history on your compressed air system and help improve system efficiency along the way. Okay, here we are with step 2, measure and quantify. So I'm a data guy. This is exciting for me, so I'm spending a little time with this one. But power flow and pressure should always be measured, and you want to measure them for at least a week, preferably longer, to obtain an accurate system snapshot. You can get other data points, such as pressure dew point, like we said. Flow you can measure in various ways, flow meter, maybe a load signal, a vacuum transducer. You might also want temperature in the room, so you want to look at those as an as-needed basis, part of your goals set up from step 1. The measurement period should include nights, weekends, or other downtime, like maybe it's 4th of July, where you have a maintenance shift but not production. And that'll help you identify any non-productive demands. You should also pick a time of year where the demand is indicative of typical production, or schedule the audit for the peak production period. If peak and off-peak production vary greatly, you might want to consider multiple audits. Remember that since you pay for kilowatt hour, you should measure true power via kilowatt meters, which are going to monitor amperage, voltage, and power factor. Loggers should record data at least every second. This could or should be faster depending on the events you're actually measuring, but certainly you can look at data averaged over a preset recording interval, say such as 10 seconds, 20 seconds, but again, it's going to be determined by your plant demand. Like I've mentioned, a suitable KPI, or that key performance index for all compressed air systems, is going to be specific power consumed. So that's kilowatt per 100 cubic foot per minute, or CFM, of compressed air used. This provides an idea of how efficient a compressed air system is running regardless of varying plant outputs. If you've ever seen a CAGI data sheet or a Compressed Air and Gas Institute data sheet, you'll see that variable frequency drive machines have typically 3 to 5 data points. Load-on-load compressors have 1 data point at full load, so that's kilowatt per 100 CFM. But we're talking about a system dynamic, so it's going to be at really any given point. Recommended system KPIs are below 21 kilowatt per 100 CFM, and they're going to vary based on operating pressure of the system. The lower the pressure, all things being equal, the lower the specific power and the less electrical energy you pay. In step 2, again, we're tasked with measure and quantify. So the best way to do that, install data monitoring equipment. The graphic at right, 10-day period of data presented together, so you can see kind of the overall patterns. Kind of getting a little ahead of myself because we're getting into step 3 about analyzing the data, but this is going to help you visualize what we're talking about with the bullet points at the left. If I simply said measure flow, power, and pressure like that last slide, what would you think of? So, now you have a kind of a visual. And now we have a graph. We can see that flow is on the bottom, broken out for each compressor in 2 different colors. Power is shown in the middle for each compressor, again color-coded to match the flows. And then the pressures in the 2 sides of the plant, 2 rooms, are at the top. Since compressor 2 was running in modulation control, flow on number 2 was measured by actually installing a vacuum transducer below the inlet valve but above the air end rotors. The discharge flow will fluctuate proportionally to the inlet vacuum, i.e. 50% vacuum represents 50% flow, and that's the way it'll nominally work unless there's some mechanical failure in the unit. A vacuum transducer could not be installed on compressor 1, so flow meter was installed at the discharge of that system prior to the distribution piping. Again, pressure sensors installed in both compressor rooms as well as kilowatt meters at the incoming power to each compressor. So we got the drive motor as well as the fan motor, so we got total power. Measured specific power, or that KPI, was just over 32 kilowatt per 100 CFM, so significantly higher than what we kind of set as a benchmark on the last step, which shows there's significant energy savings here. Understanding the dynamics here in step 3, we've documented the system, we've collected data, and now we're going to thoroughly analyze everything. So pictures, questions, goals, as well as that data, and then look for areas of improvement. So, first going back to our original hypothesis, why are we doing the audit? What are the problems we're facing with our compressed air system, etc. So what do we see in the data? Is there a varying pressure profile within the facility? Did we catch some compressor reliability issues with units shutting down intermittently? You'll see a few pictures at the right. The first at the top is a ventilation duct from a compressor. Hard to see here, but looks a bit small to me. I know it's small because it's a picture that I put in, but so we may see that this particular compressor is intermittently shutting down via the data that we collected. But we may not know why in the data, but with this picture, we can clearly see that it's probably overheating. Putting these pictures together with the data, again, going to make a big difference. Also, the picture at the top right shows a T coming straight down from the pipe. That next picture there, clockwise down, shows water at the connection point below this particular T. So this might explain product quality problems at the point of use. Further, the bottom picture shows piping after a dry tank. And this picture, this pipe could be amply sized for what they're using, but it could also be significantly undersized. So it all depends on the flow profile. You'll see this when you look at the pressure profile of the system. Other problems you should see within the data would be compressors fighting each other. However, inefficient uses of compressed air, you'll have to identify via that site survey. And you may also see high demand events within the data, but most likely, if you didn't install measurement equipment at those points of use, you may not see the same amplitude and demands back in the compressor room. So these are some of the big ticket items, but it's nowhere near all the items you could see at this step. Getting back to our case study, average compressed air supply was about 240 CFM, so you kind of slice the middle there with the flow on the bottom of the graphic at right. And the required plant pressure was only 95 psi, so we're amply meeting that with the system we have. The supply range of compressed air was about 200 to 300. And most often we saw both 1 and 2 compressors loaded to maintain plant pressure. The available compressor supply is significantly exceeding the compressed air demand. And based on the measured flow profile that we're seeing during the test, compressor 1 was capable of meeting the average demand without assistance from number 2, but was not capable of meeting the peak demand. What we can see in this chart here at right is that the units are fighting each other during normal operation. And you can see the kilowatt signatures of these units. In some cases, the kilowatts are going up and down together or close to it. In other cases, we see kilowatt for the 50 horsepower hit maximum and then stabilize, but the discharge flow varies significantly while the 60 horsepower is also throttled back. Since neither of these units are VFDs, power consumption is relatively high for the amount of flow produced. Remember, we said they were modulation control units. Notice, too, that while the pressure profiles are about the same, pressure varies more with compressor 1, as this unit appears to be loading and unloading quite rapidly. Looking a bit more at some data, when compressor 1 was either manually stopped or when the unit experienced failure, pressure in the facility dropped below the minimum required level of 95 pounds. And that's what we see just with the blue line at right, with pressure tailing down below 85. During these times, the flow meter at compressor 1 put an average about 50 CFM, so we had some backflow through the flow meter. This suggests that a significant portion of the air demand in room number 1 was actually air leakage. Also note that with both compressors online and loaded, pressure is maintained well above that 95 requirement. However, the average flow is typically below the flow for the 60 horsepower. So why do both air compressors need to be online and loaded? It's a good question. When we look further on the same chart, where number 2 is loaded by itself, but pressure is falling, we also see that there's a significant pressure drop between those two rooms when compressor 1's offline. It's between about 10 and 15 psi, suggesting that the piping network, remember we identified that as 1 1/4, 1 1/2, and 2 inch, significantly undersized. But why? Could it be that it's black pipe? Could it be that it's corroded internally? Those are things that we'd have to look at. Plus, then we have that backflow on number 1, which appears to be leakage. When pressure drops so significantly, you also have to be careful of the rating of your dryers and filters, as air quality can be compromised with these pressure drops. Lastly, in this step, we want to look at efficiency. So looking at flow, power, and pressure for each unit is really helpful as you determine which units are running most efficiently. In this case, compressor 2 is the most efficient of the two, still not really efficient at all, and that gets to, we're still at about 32 kilowatt per 100 CFM, which is extremely inefficient. Moving to step 4, now that we've analyzed the data, along with what we know from the site survey, we can look at making some improvements. We see a lot of recommendations and requests from end users for variable frequency driven units. In general, top 3 recommendations from cookie cutter audits are new VFD or to replace a compressor, adding a storage receiver, as well as adding a flow controller. And I won't go into the merits of each because there are merits for each one of these, but the idea here is to customize the solution for each plant. In most cases, again, any of these solutions will have a positive impact, but the question is, do they have the best ROI, and will they solve problems inherent with the plant? Am I just trading one problem for another? So many system assessments are going to focus on reducing compressed air consumption, and what better way to do that than fixing your air leaks? Number 1. We've already talked about piping in our case study example, but there are many times by increasing pipe diameter in the compressor room, distribution network, or to the point of use that can have a huge impact on your overall system operation. And I often say, like simply replacing compressors of one color for another and not changing anything else can lead to repeating the same problems you've already done. So augment piping is a big ticket item right there. Operating pressure, that can have a big impact on your overall bottom line. Reducing your air pressure to the lowest possible point, often referred to as the scream point, not only going to reduce your energy consumption, but will reduce your demands. If you put that pressure too low, you're going to have people in the plant screaming for more air, so hence, scream point. System pressure has a direct effect on energy consumption. You'll often hear 2 psi equals 1% energy increase, as well as 10 psi reduction can reduce 10% flow. So these represent significant savings opportunities. Getting ahead of myself here, but if you recall, pressure in the compressor room was about 105 psi, so we were operating fairly low to begin with. However, we did have the compressors fighting one another. So addressing controls, like you see on the graphic at right, that's going to help. The graphic shows a history of pressure profiles over time. So, before we had master controllers, cascade pressure profile, great way to try to keep compressors nested. So only one compressor would come on at a time, so that saves your demand charges. But it leaves you with a very wide pressure band, which ends up resulting in higher demands because all leaks are going to leak more at higher pressures. As well as the power consumption for those non-peak times is going to be higher. With the advent of a pressure band master control, which is the blue area, so next to the right, you can see that pressure tolerances are reduced. Now moving further to right with the green, you can see a master controller with a target pressure. And so now you can see where that band is even tighter still and lowering that overall operating pressure. So now looking to the far right, you can see where we actually set a floor, and then that pressure is adapted to various demands. So in short, adding a master controller can reduce your overall system pressure while providing the huge benefit of ensuring each compressor is running as efficiently as possible, as well as the overall system. Simple, easy, and something that may be often overlooked, turn it off. It's just like I tell my kids when they leave the room, turn the light off as long as your sibling's not in there, but nonetheless, turn the system off. We established that energy cost for a compressor is 3/4 of the overall life cycle cost. We also talked about that compressors are as much as 10% of all electrical energy generated in the U.S. So why run a compressor or a system if you don't need to? Look at your overall production schedule. Simply turn off your station when it's not needed. That's going to save you a lot of money. And we're going to see that here in this example as well. Further, eliminating inefficient uses of compressed air is going to help you reduce the potential of about 50% of compressed air demands because it's wasted energy. Again, using engineered nozzles here, for example, to replace perforated pipe for blow-off applications, that's going to reduce your overall demand. These same uses, they could be an integral part of your plant operation, but they could be costing you a significant amount of money. So looking at each individual use during that site survey and having an auditor who knows their way around a plant, that can really help you in this step. What else can you spy to change in your compressed air system? And we mentioned in the case study that there were two 240-gallon storage receivers. Those were decent sizes for the modulation control, and now knowing the actual operation, storage volume for there was sufficient. However, if you had different controls, load unload, VFD, or you were adding compressors, that storage volume may be severely deficient in adding that necessary control buffer for your compressors to cycle. The great part about storage is that, save for the demand drain, there's nothing mechanical. All these further points have a small or large impact on station efficiency depending on how your system is operating today. Your compressed air auditor should be well versed in what options should be considered for your system based on the walkthrough, as well as the air audit data they analyze. Notice to this point, we haven't discussed specifically new compressors. Not to say that they aren't warranted, but in general, focusing on these other items will help assure that when you're ready to replace compressors, you've gotten the most possible savings from your existing system. Back again to the case study, number one here was reconfigure the piping. The piping was a critical component in the system's optimization. Creating a closed loop allowed the proper system pressure downstream and required less work for the compressor. Without creating this loop and upgrading the system piping, I would suggest that simply changing the compressors would have resulted in the same problems. 3-inch aluminum piping was a great choice, allowing for system expansion and providing a piping network that isn't susceptible to rust and scale like the existing black pipe was. Plus, if we abandon the existing black pipe in place, this would also give rise to eliminating potential leakages. Looking at this as a step-by-step implementation, removing compressor 3 allowed for a more efficient compressor to be added, should we choose. Also, since it didn't run during the audit, its reliability was questionable. Compressors 1 and 2, they did run, and we know from the data that they can keep up with plant operation, albeit inefficiently. So keeping those machines as a backup is definitely helpful from a reliability standpoint. Next, augmenting the storage by replacing those two 240-gallon receivers with a 1040-gallon receiver is a great step. Now, I've seen receivers that are 50 years old, and as long as they're inspected regularly, these may still be in service, but consider that most receivers aren't stainless steel or galvanized or have any kind of internal coatings. And since compressor condensate can be acidic over time, rust and scale can and will build up in these tanks, and that can be very costly to your overall production and air quality. Finally, installing a 55 kilowatt or 75 horsepower rotary screw air compressor was the last step here. VFDs applied within a 40% to 85% operating range are going to be the most efficient. And that's why the graphic at right is shown to kind of give you an idea. There are drive losses and air and block losses to consider. And these are minimized when comparing a VFD to a fixed speed compressor if you stay within that 40 to 85% range. VFDs can certainly operate at higher or lower flows, but then the efficiency gain is lost. Again, the piping was that critical component in the system's optimization. Creating that closed loop allowed for that proper air pressure downstream and required less work for the compressors. Trust but verify. I've heard this saying more than once over the years, internally and also externally. In the air auditing business, post-tests are a great way to validate any system. You go through the same process as we already dictated. However, this time the auditor would be more familiar with the plant operation, as well as the plant personnel. Also consider utility rebate programs sometimes require energy savings to be verified by an additional compressed air assessment or audit performed after the new system's installed. In cases where utility rebates don't require such a degree of verification, facilities should still consider implementing some form of post-optimization assessment. All systems can be enhanced, even systems designed using an air assessment or air audit data, and that are newly installed. You put in a brand new 55 horsepower or 55 kilowatt VFD, and maybe the pressure settings are at 125, and you can really do 100. So there's various ways to look at that. When you're doing this secondary assessment or verification, don't forget to include nights, weekends, and holidays. I've had folks say, "Oh, we just want to get an hour's worth of data." Well, things change overnight. Things change week by week. So take that into account when you do your measurements. Again, take pictures so you can show that before and after to your management team. There should be nice, new, shiny equipment, and everybody should take ownership over that. Lastly, target that KPI under 21 kilowatt per 100 CFM. There are a multitude of ways to verify performance of a system after implementing changes. However, the scope of the changes can dictate how you measure. If you add a master controller, typically these devices now can stream live data at your fingertips. So in this way, you can continuously monitor your system. If you look at the screenshot at right from this post-verification performance test, or testing period, you can see flow at the bottom. That's in the green, power in the middle, which is in the blue, and then operating pressure at the top, which is in the red. When you start looking at the data, you want to look for a stable operating pressure with minimal pressure drop throughout the plant. If you've added a VFD, check whether that unit's running within that 40 to 85% of its full load. And remember, check and see what's going on during the evenings as well as the weekends. And if you see here, you've got some periods that are white in the middle, and so they've actually turned the system off most likely on the weekend or overnight one day. So, there's some found money there as well. And you can always incrementally change your system after adding a master and thereby seeing the effects of these incremental changes. So, okay, let's say, you can see here, it's a little hard to see, but it's 100 pounds there at the top. Maybe we could do 98 pounds. Maybe we can do 95 pounds. Try to get closer to the screen point. Obviously not trying to affect production, but get to a point where we're at the lowest possible energy consumption. You'll also definitely need to evaluate with your compressed air auditor how you can integrate your compressors, new, old, or any combination thereof, with a master controller. Getting back again to our case study, a follow-up compressed air assessment was performed for this particular project. The verification results showed that although the overall demand in the factory had gone up, some 244 CFM to 289 CFM, so about 40 CFM. The 55 kilowatt VFD, that efficiency was well within the target zone and 18.6 kilowatt per 100 CFM. So significantly lower than 21 and significantly lower than the 32 we started with. Average operating pressure had also been reduced by 3 pounds, so that was great. One of the 2 primary compressors was water-cooled, so we had a bonus potential energy savings there. And then the annual energy savings were verified at just over $19,000 per year, which was over a 40% reduction for overall energy costs. And that's slightly higher than the original estimate, which was fantastic. So this case study, while several years old, is certainly relevant today. In this case, simply adding a VFD compressor without augmenting the piping would have most likely resulted in the same problems occurring. And we probably would have known what those problems were if we didn't do an air audit to start with. So now what? What should you achieve after the assessment? So don't forget that your compressed air, in most cases, again, is mission critical to your plant. If it's not up and running, neither are you. The more you know about your compressed air station, the more efficient it can run and the more problems you can avoid. Keep the data flowing. Like I mentioned, you can do this via master controller, or even a lot of individual compressor controls out there can be mapped to your company network to provide data, alarms, and so on. So capitalize on that as you move forward. In summary, these 5 steps, they're going to help you understand your system. They're going to allow you to engage all departments within your facility and get them on the same page. Pairing with a compressed air expert can help diffuse internal conflicts, and they'll give you access to a wide variety of industry knowledge every step of the way. Don't forget, verify your system after you've made incremental changes or implemented any change, and then optimize it as necessary. And like I said, lastly, continuously monitor. Because most times, you never know, it just takes one button to be pushed, and the efficiency of the system can really just disappear. So keep your finger on the pulse of your system. By completing an air assessment and following up on those recommendations of the report, you should be able to cut air compressor maintenance costs by optimizing runtime and reducing excessive cycling, and as a result, improve reliability as well as increase service lifetime. You'll be able to better operate your equipment and keep those compressors on the same maintenance schedule, thereby minimizing maintenance costs associated with multiple trips. Using air audits to help qualify for utility rebate programs and pay for system upgrades. Another great opportunity there. Product scrap and waste can be improved by providing stable operating pressure to the points of use. Production equipment maintenance costs can also be lowered through improved air quality. By assessing whether existing air treatment is sufficiently selected and sized to meet the required air quality. So that should be part of every audit. When coupling these items together, you can also reduce your carbon footprint. In fact, our customers, again, typically find that a properly operating system will reduce their preventative and troubleshooting activities by as much as 30%.
Wow.
I want to thank everybody for their time today tuning into this webinar. Attendees are going to receive a copy of Kaiser's Compressed Air Assessments white paper via email, but please take a look at these additional links for more information on compressed air audits, leak detection, and best practices for an efficient system. So I know we have time for questions, so now back to you, Christine.
Yeah, thanks. No, the more you know. I love it. I wish we had the little sound effect that goes with it, but yeah, the more you know. And I'm a data nerd too, so it's fascinating to go in and see some of these numbers are just so staggering. Both the waste, the use, and the potential improvements. It's huge. Thanks so much again for the great information here, and we do have several questions here. I'll turn to number one. how do I prioritize? How do I know which leaks to fix in my compressed air system first?
Yeah, so, leaks are an interesting problem. If you can hear it, that's the one I would correct first. You can get out there and you can do a leak audit, and you can figure out what leaks are out there. It's kind of an 80-20 rule. You want to get the biggest leaks possible first because that's going to make the biggest difference. So obviously if you can hear it, that's going to be your most costly leak. So get to those first, and you can go through and do a full leak audit and kind of figure out where those pieces are. Getting back to data, if we have an off-peak time or, like say July 4th, and we've got data during that time frame, we can say, okay, the system average demand was 1,000 CFM, but during that July 4th period, it was 500. Wow, 50% right there. So now you can say, okay, you go to your boss or your procurement folks and say, okay, we need to do a leak audit and figure out where these leaks are because 50% of our system is due to leaks. Just an example, but so, getting back to it, the leaks you can hear, those are the ones you want to correct first. And you want to have kind of a plan. Smaller facilities, typically maybe a leak audit every year, every other year. But larger facilities, I would say definitely every year and or quarterly, depending on how much air you're using.
Sure. Okay. Our next question, what are the key continuous monitoring points for the compressed air system?
It's funny, you ask a data person and they can't make a decision. This is important and that's important. It kind of gets back to, what we just talked about with the air auditing. To me, the most important things are flow, pressure, and power. Most compressors now with individual controllers are going to give you the majority of that information. I think the most important thing from a reliability standpoint is alarms, messaging, and history. So those are the things, those are the key points for me. And, if I was a plant user that I'd want to know. So, I'm, plants 24/7. I'm the plant engineer. I'm there from, 7 to 3 or 7 to 4. I want to know if the compressor turns off for whatever reason for an alarm so that I'm in the know when, I get the phone call at 3 in the morning, hey, such and such went down. So, knowing the system efficiency, to a data guy like myself, that's paramount. But when you're talking to somebody on the plant floor or management and reliability and uptime, that's going to be really the most important stuff. So, general operation, load, service hours, from a service standpoint, when do I need to come out again, as well as, alarms, general alarms, warnings, maintenances, and so on. And then, a lot of these things can give you reports monthly, weekly, quarterly, whatever, on your efficiency. So, I think we covered that one.
Okay. Yeah, we got a couple more that we have time for, I think, here. Next, should only discharge pressure leaving the air compressor be monitored, or also the system pressure controller downstream?
Yeah, so I definitely have pressure at the discharge. So if we're talking about an air audit or just in general, downstream of the air compressor directly is also helpful because you can figure out what control pressures the machine's actually running at. Especially if it's an older unit and the gauge, you're not sure if it's reliable or it's a pressure switch or something like that. Downstream of air treatment is great because then you can kind of get, okay, well, what is that pressure drop across air treatment? And it's going to vary based on the demand. When you have full load, it's going to have more pressure than when the machine's off. So, you'll get an idea on that. And if you've got one large dryer for more than one compressor, then that pressure drop will vary as well. So I definitely say discharge of the air compressor or compressors downstream of air treatment. And then somewhere at the point of use, we gave the example, there was very little pressure drop, from the compressor room downstream of air treatment to the point of use. But in a lot of cases, we see that could be 10, 20 PSI. And so it's a great way to kind of prove to management that, hey, you know what, this black pipe that was installed 40 years ago is really not cutting it right now. And yes, it's 10% of our over energy, use, not a big deal per se, but going forward, energy costs are going to rise. So yeah, I would definitely have pressure at least 3 points. It could vary depending on what your high demand uses are. Maybe you have some more, but I think that, yeah, that would work.
Okay, great. Let's see. Moving on here. Have you seen or used new sonic air leak imager to help detect plant leaks?
Yeah, that's a good question. Me personally, I have not. What we do use, the leak detection equipment that's out there. There's a lot of pieces that are out there, and it does use volume, if you would, so audible decibels, and based on where you are and how close you are to that leak, it's going to give you an idea based on the noise level that it's detected. Sonic, if you would, can give you an idea on what that flow is. So yeah, I'd say you want to use that information. Not something that let's say I have experience with calculating or creating, but there are a lot of great engineers out there that do that kind of thing. So the values are going to give you relationship information. So this leak is smaller than this leak. And, like I said earlier, that 80-20 rule, when you have a leak that you can hear without this equipment, those are the ones you want to definitely correct as soon as you possibly can. This kind of equipment's great because it gives you an idea on, okay, now I need to prioritize. Okay, I fixed the top 20. Now I'm going to go to the next 20, and so on and so on.
Right. Okay. So now let's say you've got your analysis, you've done your assessment, and you've got recommendations produced from it. Is it a good idea to have multiple companies review those?
From a manufacturer standpoint, when I put that hat on, I'd say maybe not. But from a consumer standpoint, sure. You want to have 3 bids. Usually most companies say, well, I want to see what these costs or that costs are. And in a lot of cases, if you just get, let's say, a cookie cutter audit that spits out some information, you want to say, okay, well, is that what I really want to go with? Is one giant VFD the best choice for my facility? So yeah, I think from an end user standpoint, I think it's helpful if you could look at, okay, well, this is my flow profile. Don't worry about what manufacturer representative 1 has suggested to me. What do you think, and why? Mm-hmm. And so in a lot of cases, you might see, yeah, maybe in this case, the case study is a great example. We went with a VFD. It cuts what the customer wanted. It fit, their mold. They kept a couple machines as backup. Great scenario. Maybe it's better from a customer standpoint if they went with 2 smaller fixed speed machines and kept one of their old units. So there's a lot of different ways to look at new systems or really assess the situation. But the best way is to get in the plant and then get outside the compressor room and see what we're really doing with the air. So good question.
Yeah. And you made some good points about the value of, again, needing to get out of the compressor room, but also talking to different people, on the plant floor and around the facility to get their perspective. It's a time-intensive process, and great to get a lot of voices and make sure that you're really going at this in a strategic way. That being said, what are some considerations a plant might have for whether they should be taking on an assessment themselves or hiring someone to do it?
Yeah, good question. If they do that themselves, then maybe I'm out of a job. I'm only kidding. I think it really is. It's a good question. In general speaking, I don't take on projects that I'm not certain about. So, my perspective, it's always easier to hire somebody to help me figure out what the intangibles are that I'm not even going to think of. And then once you have those things, kind of an idea on what to do, yeah, certainly, you could do these things yourself. I think the problem with data monitoring in general is that it takes some significant capital and some know-how. So from a capital perspective, okay, I need to buy data loggers I need to buy monitoring equipment. I need to map those two together. I need a software package to look at it. And, DOE has some software packages out there as well that you can take data into and manipulate and create some solutions. So, there's AirMaster Plus is a great tool, and there's some other tools out on Compressed Air Challenges website. So, there's a way to do it. I'd say it's always encouraging to work with a plant and kind of set some baselines and help them figure out what are the important features. And then, like I said, if a lot of these new individual controllers and master controllers, they stream data. So, in a lot of ways, if you do the assessment, you do the audit, you make the upgrades, now the system you've got can stream data. You don't need that extra equipment, and you've got that through your SCADA system, through Modbus or whatever it might be. And, you've set tags on, if this happens, do this, send this email, contact, whatever, run this report monthly. So you got a lot of things at your fingertips, which is great. So, definitely I wouldn't steer people clear of doing things themselves. Just want to make sure that you understand what's involved with it and that you know what you're looking at, I think is the better thing.
Right.
So it's like you do your own taxes, it's great. TurboTax is a great tool. Am I missing something? Do I need to talk to H&R Block and have them look at my taxes again? Things like that. So it doesn't hurt.
Yeah, right. Methodical way. What's going to get the most? What's your ultimate goal? What's going to get you the most returns? Literally and figuratively, for talking about taxes. All right. Well, Neil, thank you again so much for joining us today. I'd like to thank Neil as well as our sponsor, Kaiser Compressors, and all of you in the audience who joined us today. As a reminder, this webinar has been recorded. It'll be available shortly for on-demand viewing. You're also encouraged to visit plantservices.com, get access to even more tools and resources aimed at helping you achieve success. Today's full presentation also will remain available for on-demand viewers in the handouts area. Now, did you like this presentation? We want to know your thoughts, and we invite you to answer our brief survey that will appear on your screen shortly. Your candid answers are not only appreciated, but also they help us craft future events. Thank you again for joining us. Thank you for your attendance. Have a great rest of your day.